In this episode of Remote College Algebra, we'll be discussing quadratic equations. Let's first look at the graphs of quadratic functions. I have 4 different quadratic functions, and they're forming that familiar arch-like shape that we call a parabola. I will mention that the Gateway Arch in St. Louis is not officially a parabola, it is a hyperbolic cosine, but these parabolas look relatively close to that shape. The basic parent function is y equals x squared, and from there you can shift it around and make them flatter and make them skinnier. The green graph over on the left has been shifted left 6 spaces and up 2 spaces, so its formula is x plus 6 squared plus 2. And the purple graph on the right, it has been shifted 8 spaces right and 5 spaces down, so its formula is y equals x minus 8 squared minus 5. The blue upside down parabola has formula y equals negative 1 times x minus 5 squared plus 25, so it's been shifted right 5, up 25, and then it's been reflected vertically. And all 4 of those can also be written in other forms. So I think that's one main point that we're going to emphasize in this video, is that quadratic equations can come in different forms. Depending on what form you're working with, you might use one strategy over another, but all of them can be graphed using the different forms. All of them can have equations solved using the different forms. I've written the standard form and the factored form for all 4 of these. Well, the exception is y equals x squared, because it is so basic. It is in factored form, it's in standard form, it's in completed square form. When I first read the formulas, I read to you the completed square form. We call that the completed square form. You might also hear it called the vertex form, because the shifting shows you the vertex. The green graph's vertex was at negative 6, 2. The red graph's vertex is at 0, 0. The purple graph's vertex is at 8, negative 5. And the blue graph's vertex is at 5, 25. You also could list the formulas in factored form. This makes sense sometimes more than other times. The green graph has no real zeros. It has complex zeros. If you were going to write it in factored form, you would write x minus 6 plus I times the square root of 2 times x minus 6 minus I times the square root of 2. But it's probably rare that you would do that. However, that is its factored form. It has complex zeros. Now, the red graph, its 0 is 0. It's the only 0. So it's kind of already written in factored form. You could write x times x instead of x squared, but, you know, it's still basically kind of in factored form. Now, the purple graph, its standard form is given here. Its factored form is given below. Now, it has real zeros, but not nice clean zeros. The zeros were 8 minus the square root of 5 and 8 plus the square root of 5. So its factored form is as shown. The blue graph, its factored form is negative x times x minus 10. And it has nice clean zeros. One of the zeros is 0 and the other 0 is 10. So its factored form makes a little more sense. Out of all 4 of these, it's probably the most useful factored form. Its standard form is written above, y equals negative x squared plus 10x. So notice the standard form kind of lists it in standard polynomial form. You list the highest power first and then the next power, so we list x squared first, that term first, and then the linear term that has x to the first power in it. That's what's considered standard form. So again, this is the standard form for the green graph. This is its completed square form. This is its factored form. For the plain parent function, they're kind of all the same. For this purple graph, this is the completed square form. This is the standard form. This is the factored form. For the blue graph, this is the completed square form. This is the standard form. This is the factored form. Now when you're solving quadratic equations, you can work with the factored form, the completed square form, or the standard form. And it kind of just depends on what you're given. If you're given the factored form and it's set equal to 0, your work's already done for you. So that's kind of the nicest kind to get. For example, if we had 27 times x minus 10 times x plus 9, and it was set equal to 0, then those three things multiplied together are only going to equal 0 if one of the terms is 0. Well, 27 is never going to be 0, it's 27. But x minus 10 could be 0, it's 0 when x is 10. And x plus 9 could be 0, it's 0 when x is negative 9. So I can just look at that factored form and say, hey, one of the answers has to be 10, one of the answers has to be negative 9. And that's true whether you have, clean integers or whether you have decimals or messier numbers. So our next example, we have x minus 3.75 squared. It is set equal to 0. Now, it's technically in factored form because we understand that squaring means you're multiplying something by itself. So this is equivalent to this factor times that factor. Both of them are 0 when x equals 3.75. So 3.75 is my only solution. It's a solution that is listed twice. We say that it has multiplicity 2 because it's a solution that shows up twice. In our next example, I have 5 times x squared times x plus 12.5. And again, that's set equal to 0. So 5 is never going to be 0, it's 5. But x squared could be 0 if x is 0. So one of the solutions is 0. And x plus 12.5 is equal to 0 when x is equal to negative 12.5. If I put negative 12.5 in for x, then that factor will equal 0. So this equation has two solutions, and they're kind of obvious by looking at the equation. Now, if you have a factored form, but it is not set equal to 0, do not just jump to the conclusion and write down, in this case, I would not say that the answer is 7 and negative 2, because that's not going to be true, okay? I don't have the factors set equal to 0, it's set equal to 10. So if I plug 7 in here, it's going to equal 0, not 10. If I plug negative 2 in here, it's going to equal 0, not 10. So we would have to do some other work to actually solve that one. So again, factored form, when it's set equal to 0, easy peasy. You just kind of look at the factors and reason out what the zeros are. It kind of is staring you right in the face. Now, the next form we're going to talk about is the completed square form. And in the completed square form, you're basically focusing on, hey, I've got something squared, and you're trying to undo that square. So our simple clean example here, I have 16 equal x minus 2 squared. So take the square root of both sides, and what that accomplishes is the square root cancels out as the inverse function, the square. Notice when you're squaring something, what was being squared could have been negative or could have been positive. So over here, I really should acknowledge that this is 4, or it could be negative 4. And either way, that would then equal x minus 2. Now I have two solutions. One solution is 4 plus 2, or 6. One is negative 4 plus 2, or negative 2. Those are my two solutions. If I plug 6 in, 6 minus 2 is 4. 4 squared is certainly 16. If I put negative 2 in, negative 2 minus 2 is negative 4. However, negative 4 times negative 4 is positive 16. So my two solutions are 6 and negative 2. In the next example, I have 17 times x minus 5.5 squared. Now, I could look at this as factored form, or I could look at this as completed square form, but either way, I'm going to just see that 5.5 is the answer. If I divided both sides by 17, I would get 0 on that side. And then if I undid the square, I would get x minus 5.5 equals the square root of 0, but the square root of 0 is 0. And we can see that then x is equal to 5.5. So I put that one in because it technically kind of falls in between factored form and completed square form. It probably was easier to just kind of look at it and think about it in terms of factored form. In the next example here, I do have completed square form. I have a parabola whose vertex is at 3.5, 10, and I'm trying to isolate the square. So start from the outside in. I want to undo adding, so I will subtract, and I get negative 2 times x minus 3.5 squared equals negative 50. Then keep working from the outside in. I want to divide by negative 2, so x minus 3.5 squared would equal negative 50 divided by negative 2, which is positive 25. So that then gives me x minus 3.5 squared equals 25. I've isolated the square, so I can undo it by taking the square root, and whatever I do to one side, I have to do the same thing to the other side. And remember, when something was being raised to an even power, 2 is even, what was being raised to that power could have been negative, or it could have been positive, and when you raise it to the even power, you get positive 25. So 5 is an answer, or negative 5 is an answer. So I then have the equation x minus 3.5 equals 5, or x minus 3.5 equals negative 5. So then x is either 8.5, I added 3.5 to 5, or x is negative 5 plus 3.5 will be negative 1.5. So those are my two solutions. And if I plug both of those numbers in, if I plug 8.5 in, 8.5 minus 3.5 will be 5. 5 squared is 25. Negative 2 times 25 is negative 50. And negative 50 plus 10 will be negative 40. And then same if I plug negative 1 in, sorry, 1.5. Negative 1.5 minus 3.5 is negative 5. But negative 5 times negative 5 is 25. Still get the negative 50. Still add the 10. Still get the negative 40. Now this next example is not going to have as clean a numbers, but the principles that we're talking about are going to still apply. I'm going to try to isolate that square, and so I want to add 1/2, and when I add 1/2 I cancel the subtraction 1/2, and whatever I do to one side I do to the other side. Whoops, I got ahead of myself. I was adding 1/2, but 1 plus 1/2 is 3/2. So sorry, I got ahead of myself there. Okay, so then I want to get rid of the multiplying by 3/4, so I'm going to multiply both sides by the reciprocal. On this side I have 3/2, so if I multiply by the reciprocal of 3/4, that is 4/3, and hey, this kind of cleans up nicely. I get 2. So then x plus 4 squared equals 2, and I want to undo that square, so the same idea applies, I just don't have a perfect square. So if I undo the square on the left side, I will just get x plus 4, and then the square root of 2, or negative square root of 2, is what I get for the right side. So x plus 4 is either the square root of 2, or x plus 4 is negative square root of 2. X then is negative 4 plus the square root of 2, or x is negative 4 minus the square root of 2. Notice I get two conjugates as my solutions. Those solutions are similar form, but one has plus square root of 2, one has negative square root of 2. They're conjugates. If you're given standard form, you have some options, and it just depends on the coefficients that you have, if one option will be better than the other, and sometimes it's your own personal preference. Here I have 16 equals x squared minus 4x plus 4. It's actually that same equation that we had in completed square form. I'm just now showing it in standard form. So in this case, I'm either going to factor or I'm going to use quadratic formula. Either way, whether I factor or whether I use quadratic formula, I have to have the standard form set equal to 0. So that's the very first thing to do no matter what option you're going to take. So I subtracted 16 from both sides, and I get 0 equals x squared minus 4x minus 12. Now, due to the coefficients being nice and clean, and this one factoring nice and cleanly, that's the option I'm going to take. I'm going to notice that, hey, negative 6 times positive 2 will equal negative 12. And also, negative 6 plus 2 is negative 4. So x minus 6, x plus 2 factors nicely to give me x squared minus 4x minus 12. And I can easily pick out my answers. 6 is one of the answers, negative 2 is one of the answers, and those were the same solutions we got earlier. Okay, so we're not going to get different solutions doing a different way. We're going to get the same solutions if we do them correctly. In the next example, it is actually that second example we did in completed square form. I've just now written it in standard form. Okay, so we're solving this same equation. So remember, our answers is 5.5. But when it's in this standard form, that's not so obvious, okay? So that kind of was an example how the completed square or factored form is more helpful sometimes. But if we were given this form, I can't look at that and say, it's going to factor nicely, so I would use the quadratic formula. This video is not about where the quadratic formula comes from. That topic actually should have been covered in your intermediate algebra class, so I'm just going to state what it is. So the quadratic formula says that your zeros of your quadratic equation are given by the opposite of the linear term and then plus or minus the square root of that linear coefficient squared minus 4 times the leading coefficient times the constant. And that whole entire thing is divided by 2 times the leading coefficient. So for our example here, negative 187 is the linear coefficient, is the b. So positive 187 will start off my numerator. Then plus or minus, I'm going to square 187. Now I know that b is negative 187, but we're squaring that value, so it doesn't matter if you put negative 187 squared or positive 187 squared, they'll both be the same thing. Then minus 4 times a, the leading coefficient. Now here it does matter if a or c is negative, okay? I mean, you do need to pay attention. They're both positive in this case. And then that whole entire thing is divided by 2 times 17. And I would, have to do some calculation, because multiplying 187 by itself and multiplying these together would be kind of messy. But you know what's going to happen is that will turn into 0 for this particular example, okay? I mean, if you want to check it, you can, take 187 squared and subtract 4 times 17. Here, we can go ahead and do it. So we have 187 squared, and then minus 4 times 17 times 514.25. Is that what we had? Yes. And I didn't lie, you get 0. Okay, so my solution is just one number, 187 divided by 34, and surprise, surprise, 187 divided by 34 is 5.5, and that's the solution we got earlier. Okay, so doing the quadratic formula on this one gives us the same solution, but we were given a different form. So here, you know, it was not in factored form, so we just couldn't obviously see the answer was 5.5. Now that third example that we did, -2, the quantity x minus 3.5 squared plus 10 set equal to -40. In standard form, it's going to appear like this. Okay, this is the -2 times the x minus, was minus 3.5. Yeah, minus 3.5 squared is equivalent to this, and then it was set equal to -40. Once again, I would use quadratic formula because it doesn't jump right out at me that this factors. But I cannot use quadratic formula if it is not set equal to 0. So first I have to set everything equal to 0. So subtract 14.5, add 40, that gives me 0. And if you combine -14.5 plus 40, you get 25.5. So -2x squared plus 14x plus 25.5 is equal to 0. Alright, so again, I would use quadratic formula because it doesn't jump right out at me that it factors. So the b term is 14, so we're going to put -14 plus or minus b squared minus 4 times a. Now a was -2, so don't forget the negative. And then 25.5. And then 2 times -2. Again, don't forget the -2. And if I take 14 squared, which is 196, and I subtract 4 times -2 times 25.5, I obtain 400. Okay, well 400 is actually a nice perfect square. It's 20 squared. So the square root of 400 gives me plus or minus 20. And if I take -14 and I subtract 20, I get -34. -14 plus 20 is 6. Whoops, I should write or. And the two negatives cancel out here, and 34 over 4 reduces to 17 halves, and 6 over 4 reduces to 3 halves. So my two solutions are 17 halves or -3 halves, and we got 8.5 and -1.5 before, and those are the same results. So again, when we did the problem earlier, we got 8.5 and -1.5. Well, those are the same solutions. The other example that we had, the one that had the fractions in it when it was written in completed square form, if you were going to look or be given or look at that problem in standard form, it's sort of in standard form here. I know the 3/4 is factored out. If you multiply the 3/4 through, this is what you would obtain. So, you know, kind of depending on which one of these you were given, you might have a different first step. If I were given this form, and that's what I started off with, I would actually multiply both sides by 4/3. And what happens is the 4/3 cancels out multiplying by 3/4, and over here that nicely turns into a 2, and so you end up with x squared plus 8x plus 16 equals 2. Now, if I were given this form initially, I would probably multiply the whole entire thing by 4, and that would give me 3x squared plus 24x plus 48 equals, and then 4 times 3/2 would be 6. And so this is a multiple of what we got from above. So notice that, you know, these are equivalent to each other. It's just take this and multiply it by 3 and you'll obtain this up here. Now if I saw that, I would maybe say, okay, I think I'll use the quadratic formula. If I got this, I would maybe pause to see if it factors nicely. Either way though, I probably would divide this whole thing by 3. That would be my next step, and I would get this anyway. So x squared plus 8x plus, now 16 minus 2 would give me 14. Okay, why I'm doing that is because if I factor, or if I use quadratic formula, I have to set it equal to 0 anyway. Okay, so once again, if I were given this form up here with the 3/4 out in the front, I would multiply by the reciprocal. That divides out the 3/4, and this side cleaned up nicely to 2, and that gave me this. If I were given this form initially, I would probably multiply all of these terms by 4, which is legal to do as long as you multiply all the terms by the same thing, and that ends up giving me 3 times what we have down here. If I obtained that, I could just subtract the 6 and start doing quadratic formula. I would probably notice that all of these are a factor or a multiple of 3, and I would factor out the 3, and I would get what we have down here. Then you have to set it equal to 0. I don't see that it factors nicely, so I'm going to use quadratic formula. So -8 plus or minus the square root of 8 squared minus 4 times 1 times 14 over 2 times 1. That gives us -8 plus or minus. And if you find 8 squared is 64. And then we had minus 4 times 1 times 14, and that gives us 8. Okay, so underneath the square root is 8. That's called the discriminant, by the way. The value that's underneath the square root is called the discriminant. And cleaning that up, -8 divided by 2 plus or minus the square root of 8 is the same as 2 times the square root of 2. And I get -4 plus or minus the square root of 2. Those are my two solutions, and that is what we obtained when we did it earlier. -4 plus and minus the square root of 2. So again, the point of this video is to make you aware that you can deal with quadratic equations in 3 different forms. And you might just be given forms, and the form you're given might dictate what's easiest. Sometimes it's going to be personal preference, but all of the forms end up being equivalent. All of them give you the same solutions. All of them give you the same graphs. The last segment of this video is to relate graphs to equations, and all graphs, the solutions to equations are the intersections. So these two graphs, y equals 25 and y equals x squared, create the equation x squared equals 25. I'm just going to use the simple square root principle, and I will take the square root of both sides, and I can see that I have two solutions, -5 and +5. So that's just an example of straightforward what the graph looks like for a square root principle problem. In this graph, I have the upside down blue parabola, and here's its completed square form, here's its standard form, and depending on which one you were given, you might solve the equation either way, but you are looking for the zeros, so you're looking for where it crosses the x-axis. In factored form, I would just factor an x out, and we can see that one of the solutions is 0 and one of the solutions is 10, and we can see that in the graph. By the way, if you're given the graph and you're asked to solve the equation and you can just see right from the graph what the answers are, that's a perfectly fine way to solve the equation. Here we're just trying to relate the algebra to it. Now if I were given the completed square form, I would subtract 25 from both sides, then I would divide by -1 or multiply by -1, and that gives us x minus 5 squared equals 25. Taking the square root of both sides, I get x minus 5 is 5 or -5, so x is 5 plus 5, giving us the 10. Or x is -5 plus 5, giving us the 0. So factored form, completed square form, both pretty clean. 0, 10, your two solutions where you're crossing the x-axis. And then the last equation is our green parabola intersecting with a line. Okay, so we can see that there are two intersection points, but I can't easily see what they are. I could estimate, but I can't easily see what they are. So here's the equation given in completed square form. Here it is in standard form. Now, if I were given completed square form here, I would put it in standard form because this is not going to help me at all. If I subtracted the 10 to collect it with the 2, that's fine, but then I still have an x term over here, and it's completed square form. I'm going to have to put it in standard form to get anywhere anyway. So now that it is in standard form, I would multiply everything by 3. So I would get 3x squared plus 36x plus, let's see, 3 times 38 would be 90 plus 24, so 114. And then -2x plus 30 is what we get on the other side. Now I'll collect like terms. So 3x squared, add 2x, so plus 38x, and then subtract 30, and if I subtract 30, I get 84 when I subtract from that 114. Okay, so can't see that it factors right away, so good place to use quadratic formula. Opposite of the b term, plus and minus, b term squared minus 4 times a times the constant over 2 times 3, and -38 plus or minus, and figuring out what we have in there, 38 squared. Whoops, it would help if the calculator was on. 38 squared minus 4 times 3 times 84 gives me 436. So my discriminant, the number underneath the square root, is 436. Again, not a recognized perfect square. So I think I'll just leave the solutions like that. I mean, we technically have two solutions. One is -38/6 minus the square root of 436 over 6. And then this solution has x value. Again, you could also think of it as points with an x and a y, but the x of that point is this, and the x of this other point is -38 over 6 minus the square, or sorry, this one's plus the square root of 436 over 6. All right, and again, probably we'd look at them in decimal form anyway. Okay, so that's a pretty solid review of all kinds of things to think about in terms of working with quadratic equations. But when it comes down to it, you're either going to be working with completed square form, also called vertex form, standard form. That's when you either factor or use quadratic formula, but if you're solving an equation, make sure you set it equal to 0. And then factored form, if you use that if you're definitely if it's set equal to 0.